Hello and welcome to all the viewers. So in this video we will going to discuss about topology optimization of rectangular beam using ANSYS mechanical. So this slide represents the learnings in this video. Very first we will discuss about the problem statement of our present video. So here we will going to see the rectangular beam topology optimizations, and then we will move towards our ANSYS learning part. So there we will discuss about how to create a geometry in Spaceclaim or design modeler. Then we will discuss about how to perform the static analysis, and then we will move towards the actual part, that is topology optimizations. And then once our static analysis as well as topology optimization is performed, then for the optimized beam part we will going to perform the validation analysis. So this slide represents the actual problem statement of our present video. So here we need to perform the topology optimization of triangular bracket subjected to point load. So we need to refer the below figure. So if you see that this is nothing but your rectangular beam having a dimension of 400 by 25 by 3000. So here 400 is nothing but the height, while 25 is width and 3000 is nothing but your length. Okay, and if you see that it is supported, you can see that fixed support at the both the ends, as well as you will find the middle point load of 1 e raised to 5 we need to apply at the center location of the beam. Okay, so for this rectangular beam we can check that for a middle point load what amount of material we will going to remove from this respective beam. So similar kind of methodology will going to apply for all kind of brackets, or you can say the beams, rectangular plates which may have a fixed support or simply support or cantilever beam supports. And then if you want to optimize, then you can follow the same methodology. So now before moving to the current problem, I will take you in the our graphs engineering channel. So here you can see that we have already covered a few of the videos, or you can see the playlist. Here you can click on the topology optimization tutorials. The first tutorial we discuss about what is the introduction, or you can say the background of topology optimization, the types of topology optimization, then you will find the physics as well as objective, what are the various constraints, then practical example as well as workflow. So all this we had covered in our first video, that is introduction of topology optimization. In addition to that, you will also find our another video on the same topology optimization, that is you can see this is nothing but further a triangular bracket, and here you can see for the respective fixed and loading condition we perform the respective topology optimization, and you can see that what is the optimized shape we obtain after perform this respective simulation. So you can go through that. We will put the link in the description. Okay, now we will move towards our actual problem. So let's see that the very first you just need to drag and drop your static structural, then you can right click and you can open your geometry in your respective either design modeler or your Spaceclaim. So we know that the dimensions, like first of all what we can do now, we can use the standard cross section, and before that just check the units, just make your respective unit preference, then go to concept and click on the rectangular. So here as we know that our dimensions are, the height is 400 while the width is 25. Okay, and for this respective profile we can extrude that up to the respective length of 3000 mm. and then let's generate. Okay, then right click, zoom to fit. So if you see that we had obtained 3000, that is nothing but your length. You can see furthermore here 3000, and you can see that the vertical height of 400 while the width of 25. Okay, so as we know that we have a point load at the middle of the location, then what we can do now, we can select that two edges and we can use split edge option so that we will have a point at the middle locations generate. So if you see that now these two lines are splitted with the factor of 0.5. Now if you see that when you keep this vertex option, display vertices option, then you can find that we have created the middle, we have splitted the edges. Okay, the purpose of this that we can now apply the point load at this middle point locations. Okay, once your design modeler geometry is done, then you can right click over here and then you can edit geometry in your ANSYS mechanical. So very first we can perform this static simulation and then we can carry this result to the topology optimization. Now our geometry is open in ANSYS mechanical. So now let's define the loading as well as boundary conditions. The very first we'll try to mesh this. So as we know that the dimensions, so based on that you can define the local sizing. So right click, insert, and then here you can define the sizing. So just select that respective body and here you can define by default, as we saw that it is 150, but here we will going to put a 50 and let's do the mesh with this respective sizing. So based on mesh you will find that your geometry optimization will going to vary. So here what we can do now, we can define the each sizing further. So let's put here two elements and let's further right click and update the respective mesh. Now you can see that we have created two elements across the thickness. Now let's define the next step, that is loading and boundary conditions. The very first we are going to define the fixed supports. So as we know that we have fixed supports at the ends. So what we can use now, we can directly define that conditions on the element face. So if you know that this is the latest version, so here you have an option called element face base fixed default. So you can see that here you will find that we have selected the four elemental faces as a fixed support. So fixed supports, as we know that, is nothing but all rotational as well as translational degrees of freedoms are fixed. Now the next step we can apply the forces. So here as we know that we can't apply forces on the nodes. So let's try this. So here you can see that we can't select and we can apply the forces on the nodes. So for that we need to use nodal force. So in order to use this nodal force, we first need to create the name selections. So for that, so now let's create the name selections. Right click, insert, and then you can create a name selections for the respective nodes. Okay, so let's see the midpoint nodes. For that, if you remember, we have created a split. So we will going to select these four nodes. So basically it is second order, so that's why you will find that mid-side nodes are also available. So you just need to apply, and this is what the name selection we created, and just select this name selection over here. Okay, so now here you can see the option called divide loads by nodes. So no need to worry about that, it will automatically divide that whatever the load you will going to apply. Okay, if you don't want to apply, if you want to apply for the respective node, then you can keep this option no. So that is the flexibility over here. So let's put 1 e raised to 5 and then define minus 1, so that direction will be in negative y directions. So now we had applied a fixed support, we had applied the nodal force, and then for this we can simulate the simulations. So here we are using by default material that is nothing but your structural steel. So this material, if you know that it is already available in engineering data, so by default you can use this material. If you want to use another material, you can either define from engineering data source or else you can define by yourself. Okay, so let's go to mechanical and let's try to solve the simulation. So once simulation is performed, then we can do the next step, that is topology optimization. So if you see that we had obtained the results for the respective forces and stresses. So let's evaluate the results and let's check the deformation. So if you see the deformations, Nova FM, we will have somewhere here, and from stress point of view, so if you see that we have a great amount of margin, let's put 138 as the limit. So you can see that the very few reason, this is the localized reason, here you will find the stress in the range of 192. Remaining all other reason, you will find the stresses are well below. So from this you can easily figure out that we can do the optimizations. Okay, so based on your stress result, you can easily identify whether you need to go for optimization or not. So basically it will help to reduce the over design of the structure. Okay, now if you see this reason where you will find the blue reason, that part can be easily removable. So let's go now to our topology part. So here, in order to perform the topology optimization, you just need to drag and drop and just carry the results to your system. So now if you see that it got disturbed due to these connections, but no issue. So you just further solve that, and then you will find that that deck is already available. So here the very first option you will find, this is what the optimization. So optimization reason, you know that we need to optimize this rectangular beam, so that's why we selected that beam, and then here we define the objective to minimize. So basically we need to minimize, and then next we can define here, we can minimize the mass by 50%. So here you can define your respective mass details. You want to keep 50%, then you can keep 50. If you want to increase like that, then you define from this respective bar. Okay, now here there are furthermore few responses are available, like if you want to optimize by mass, volume, center of gravity, moment of inertia, and if you want to optimize based on your von Mises, local von Mises. So there are different criteria are there. We already explained this in introduction of our first video for the topology optimization. You just need to go through that, you will come to know. So all these response constraint you can provide over here. Okay, now let's do the optimizations for this respective. So here in analysis setting, you can see that the number of iterations it can perform, that 500, this minimized normalized density as well as convergence accuracy. So you can by default you can keep as it is, there is no need to change. There are few certain things are there where we can use this. When we have complex structure, in that case we can use this, and there are further manufacturing constraint. If you want to include, then you can include that. If you want to exclude, then you can also include. Furthermore, there are minimum member size are available. So basically when you are, take an example of base frame where we have a different kinds of member, so there you can even define the sizes, minimum number size for the respective steepeners. Okay, so there you can use these options. So here there furthermore we have non-linear controls as well as few output controls over there, and in addition to that you will find further analysis data management. So you can keep by default whatever the options are there. Okay, and then here on a solution you will further find that the very important parameter, like as we know that we need to do the validation, for that it will generate the STL file. So from here you can keep that option yes, so that you will get the STL file. Okay, then let's do the simulations. So it will take some time to get the solutions. So now if you see that we had performed the optimized solutions and then we obtained the result. So here you can easily figure out how your shape is. So from here the toolbar you can easily check the threshold. So like if you want to keep, you can see these values. So by this you can play with this and then you will come to know. So let's put here 0.5, and for that 0.5 you will find that here the color code you can find that remove this 0 to zero point 0.4 and the marginal is 0.4 to zero point 0.6 where we keep 0.6 to 1. So basically we define 50% material to keep, so that's why you will find the shape like that. But if you know that when we have a beam kind of structure like this, then you will find this bottom face will not going to, here you will find some sort of constraint in vertical direction. So that what we can do now, we can define that insert and here exclusion reason. So basically what we are doing now, we want this bottom face so that we will keep this surface in contact with the vertical member. So that's, in that case we can define insert and here exclusion reason, you can define the respective face. So let's put this apply. So now we had to define the respective face. So let's simulate the solution. Okay, so like that you can define the exclusion reason within your complete geometry. So what are the plot you want to keep mass for that respective face, edge or point, you can use this option called exclusion reason. So now if you see that our simulation is performed, and now after adding this exclusion reason, what it does, it does not remove the material where we define that in from the exclusion reason. Okay, so like that you can define the exclusion in your respective geometry. Now if you see that this is the additional material where software has already removed. So basically it got reduced. If you see the initial geometry is like this, and then after performing the optimization we found that our geometry will be like this. So like that you can see, you can, if you, the practical example of this is like if you see, if you have seen that bridge structure, you will find that the both bridge structure sides you will find some sort of structure. So basically no one will going to use a complete structure like this. It will unnecessarily increase the weight. In addition to that it will also increase the cost. So all these parameter we need to keep in mind, and based on that we can decide whether we need to go for the optimization or not. So if you see that here after doing optimization we can drastically reduce the cost as well as we can save the good amount of material. Okay, now the next step is that whatever the structure we obtain, for this structure we need to furthermore we need to do the check that is called validation simulation. So for this respective nodal force we need to apply this respective nodal force on this optimized geometry, and then we need to check whether this optimized structure will going to sustain or not. So basically this is called as a validation. So there furthermore you can even check the topology elemental density. So it is as similar to that, but here you can check the respective elemental density. Okay, so you, based on the element you can easily identify which material I need to keep and which material we need to remove. So let's do the next phase, that is validation. So in order to perform the validation, just right click over here and you will find option called transfer to design validation system. So you just need to click over that. So it will directly connect to your another static structural module where you can do the validation. Okay, so if you see that here it directly got connected to model, but we want that to be imported into the Spaceclaim so that we can do further the geometry editing. Before 2020 you will find it directly connected to the geometry like this. Okay, but don't know with this respective new version we need to check, or that might be the debug with this respective version. So no problem for that, you just need to drag another system and then you can connect with this, and then right click, you just need to update your previous model, and then you can drag that geometry to your respective Spaceclaim. Okay, now let's refresh over here. So now if you see that our geometry is connected to the validation date, so here you just need to edit geometry in a Spaceclaim. So basically what it does, the STL file, if you remember, we saved that STL file will going to carry forward in a Spaceclaim, and that the shape will look like this. So for this you will find the facet geometry, and we can do furthermore a fine tune in order to perform. So now if you see that our geometry is open in ANSYS mechanical, uh, sorry, in Spaceclaim. So here the first you will find that this is nothing but our original geometry, and the next one you will find that this is what our optimized geometry. So let's suppress this original geometry, and here if you expand that you will find the facet. So if you right click you can convert that merge faces. So basically it will convert all the faces into the solid, and even you can directly perform the simulation on this. But before going to simulation you can find that there is some sort of zigzag shape, so you just need to do a fine tuning over here so that you can make a structure manufacturable. So let's do Control Z further, and here for this respective facet we can do some other fine tuning. So let's go to your sketch, select the plane view, and here you just need to select the rectangle, select all the edges, and here you will find the option called copy. Just copy that and you just need to paste. Okay, so what it does, it just created the curves. Now for this respective curves, select all the curves, and here you can see the option called repair. So we can repair that with the help of fit curve, and here you just need to keep the correct tangency. So basically it will, you will find that this whatever the red dots over there, that will going to be corrected with the help of tangency. Now you can see here generate, and there furthermore option called curve gaps. So first select this curve gaps, if there then you can create that respective curve gaps. Okay, now let's go to the design, and in design we can perform the remaining work. So let's see here the whatever the shapes are there, we can delete this respective shape and we can directly connect that. So you just need to delete this. Okay, and then just select the line like this to this point. Similarly here you will find there are different irregular shapes that. So what we can do now, we can define some of sort of fillets. Okay, now here also you can define some fillets. So you just need to remove unwanted lines, and then furthermore you can define over here the fillet. I am just doing some sort of fine tuning to the structure. Similarly over this point, okay, and the last one over here. So here you just need to drag correctly and then connect these two lines, right? And furthermore here we can define the fillet. Now you can see that here, just trim these lines and create a straight line over here, Control J. So you just trim these lines and just connect simply like this. Okay, now if you see that our fine-tuned geometry is ready. So furthermore you can even define some sort of sections if you want. Okay, so let's go to pull now option. Now we can create a 3D model. So just pull this face, and here you can define the dimension of 25. Okay, and here you will find that we have created a respective solid. So let's suppress all these bodies, suppress for the physics. You can delete this, and now this is the geometry which we're going to use for our simulation. Okay, now let's do furthermore. Go to design, select. If you want you can split, and here you can define the middle point by putting 50, and here also you can define 50. Okay, so now if you see that these are the middle point which we created to apply the loads. Okay, now let's go furthermore to mechanical, edit. So if you see now our geometry is open in mechanical. This is nothing but the optimized geometry. So very first we will define the sizing. So let's put the same sizing what we consider for the initial model, that is 50, and then let's define the two elements across the thickness. Insert sizing. Here we can define the two elements, and let's do the mesh. Now you can see that mesh is somewhere like this, but that is okay. We will not go. We will just apply the very force, that is nodal force, and for that we can create the name selection. So name selection, and if you know that we can select the respective nodes. So somewhere here 1 2 3 4 5. So let's select that 5 nodes over here. We have selected 5 nodes. Now let's apply the same. Let's apply -1 e raised to -5. Okay, and then the next phase is just to apply the boundary conditions. So let's insert and apply fixed support and then solve the simulation. Okay, so we can easily cross check. You can even further do the fine mesh if your stress equivalent stress, this evaluate the stress. So now if you see, the deformation is 1.4 and the stress value is 261, which is nearby over here. And let's check over here in this model. So his stress is 192 because of the mesh is also good. Let's put 138 and you will find that the stress in the range of 23. So similar stress range you will find over here if you probe, see somewhere. Okay, so you just put 138 over here and then you will find that with this also, if our allowable is 138, so most of the structure except this, you will find that well below the yield limit, or you can say the allowable limit. So if you want to do further fine mesh, you just define the mesh sizing. So here you can play with the sizing, you can define the minimum size. Let's update and then you can check for that respective mesh size what is your results. So as you change the mesh, you will find that your node will going to be disturbed. So we need to further select the nodes and furthermore we need to select the element faces. Okay, so we compare original model with the optimized model. We found that stresses are well below 138 megapascal. So even you can see the deformation levels is also okay. Even stress levels are, if you put 138, you will find that except the localized region, our structure is as similar to the this one. So it means that we can have a scope of, we saw that initially there is a scope of optimization. Based on that we did the optimization and we found that we had a reduce of 50% of mass, so that it's drastically reduced the mass as well as it saves the cost of the our structure. Okay, so that's it guys. Let me know your comments. I will be there to help you. Thank you. Bye bye. Take care.